engineering is applied physics and math. I'm Ingo Suliaks. I'm an electronics engineer. My background, I have a degree in computer and electrical engineering. What do I do here? I evaluate, test, and repair or replace aging electronics, mostly for military aircraft.
So do you do anything around Coulomb's law?
Well, Coulomb's law, we use it as applied to capacitors mostly. So usually, by the time we're using it, we just use equations and models that deal with electronic circuits.
Capacitance, like what are some applications?
Well, almost all of our circuits use capacitance as a component, a capacitor as a component to as part of the circuit. So usually frequency-dependent circuits like capacitors are used. We use this isolation or as energy storage circuits.
Why is it important that capacitance only depends on epsilon?
It's like a test. I don't know. Do you have an answer for that one?
Yeah, epsilon I think is the dielectric factor. So
Yeah.
we don't deal with it straightly, but different materials have different dielectrics, and therefore we get different capacitance values.
Right. So like each one of the capacitors uses different materials. So they'll have
Ceramics,
different
diamonds.
characteristics. So some capacitors will be really big for their capacitance, but they might have a higher voltage rating or depending on what you do with them.
Okay.
I mean,
Big guys like this.
yeah, I mean,
Put
so
that
like
in the camera.
a
Bring it in the camera. Explain.
right, so huh?
Explain.
So this is an electrolytic capacitor. It has like a mat with a sort of a liquid that it uses as an electrolytic. So this is like a pretty large capacitance.
Okay.
And then we use capacitors that also use air as a dielectric,
Oh wow. Okay.
but not. I don't think anything we're currently using, but like definitely in radio circuits we use air capacitors. Okay, so this would be like a ceramic.
Ceramics.
So these are ceramic capacitors. They're very small.
Oh wow.
60 cal, 30 cal.
So the trade-off is you could build a capacitor like this with ceramic capacitors, but it'd be very, very expensive. But it's sort of changing, technology is changing. So at some point, so ceramic capacitors are almost perfect in terms of characteristics. But they're
Okay.
very expensive. So like
That's good.
air dielectric capacitance, those capacitors tend to be very large
Keep going.
because the gap has to be large, otherwise that could get argued.
What about Kirchhoff's law?
Yeah, I mean, it's a relationship between current and voltage and resistance, so we use that all the time.
Okay.
But,
Can you give me an example?
if we want to, well, I mean, the wire is an example, right?
This?
Right. So when you run current through it, there's a specific amount of resistance per unit lane. So there's actually a voltage drop, which you can calculate with Kirchhoff's law. So when you're designing like a power supply, you have to take into account how long the wire is, because it'll offer a voltage drop between the power supply and the thing that's kind of used in that other. So Kirchhoff's law, for example, lets you calculate that voltage drop.
Do you ever have to change the current in any way?
But yes, we deal with current all the time. Power supplies, for example. Right, so wire sense. So power supplies. So for example, this is like a power supply that can deliver a lot of current. that we use for some applications. And for other applications, we use power supply settings for load current. And so some of the circuits are current mode circuits, so they rely on a constant current source to operate, while other circuits are like constant voltage circuits, so the current changes depending on the power requirements. I don't know, if you want to know about current, as Derek pointed out, like, wire size is important for different current capacity.
Like the
current
flow
capacity.
of current? Like does
What's
it like the flow of current?
Well, it's important because wires are not perfect, so they have resistance. So as current flows through a wire, it heats up the wire. Right? So if you have wire with very thick cross section, there's very low resistance per unit length, and so it'll heat up less per unit length than like very thin wire with the same current.
Yeah.
So we have like rules and guidelines that we use when we're designing with current to decide what wire size we use.
Oh, okay, that's cool.
So like there'll be like a table, for example, that if you want to run like 10 amps through this wire, and you want to minimize the temperature rise in the wire, we use this kind of gauge wire. For example.
Got
Same
it.
when you're
Got
designing
it.
circuit boards, it's the same thing. Circuit board, but like the traces on the circuit board also kind of define the current carrying capabilities because they heat up, and once they heat up, then the adhesive in the circuit and the fiberglass melts.
Okay.
And then
So how do you prevent it from heating up?
you have to make sure that the wire, the thickness and the width of the trace is wide enough, it has enough cross section to carry the current that you expect to carry with the minimum temperature rise, and try to minimize the temperature rise within an acceptable limit.
Okay.
So when you design this, with modern CAD programs, you can just kind of tell them, you want to use 10 amp, and then you can kind of, calculate what the thickness of for a given thickness, they'll calculate how wide the trace needs to be.
Okay.
So when you're designing it, it'll tell you that, oh, this trace is too small.
Yeah. What about like AC and DC current?
Yeah, we use that all the time. And RF, which is like a really high frequency AC.
Oh, really?
Yeah.
Oh.
So that's like, for example, what I'm working on right now. So any kind of radio device is basically AC at a very high frequency. So, and in terms of power, a lot of our stuff is usually like DC, because that's a primary power source in aircraft for electronics, but sometimes we also use AC circuits stuff for power. So,
Nice.
more often than not, we convert AC into DC because it's more convenient for radios, for electronics.
Why is DC more convenient?
I think it's a good question. I mean, you can certainly make some of it work with like AC power too.
This is what
But,
you
we do have some things that where we do a lot of AC designs. Like Derek was working on an accelerometer, which is AC power, but it uses the characteristics of like how the phase is shifted in the output to indicate, like the direction of the acceleration. So that circuit would have a lot of AC in it.
Okay.
But most electronics like DC. It's just kind of the common design.
Yeah. Okay.
That's we don't use DC.
Yeah. What
One
about
less.
what was it? RF?
RF.
Yeah.
It's a special version of AC.
When do you use it?
When you use it for anything radio.
Oh. Okay.
Anytime you need to bridge between two things that are not connected physically. So it's kind of like a transformer, but over long distances. So that's where kind of like Gaussian law comes in, where like a transformer is a magnetically coupled device. A radio is, depending on how, because they're related, they're really kind of like a Gaussian thing. Like, so you have electric fields that change at the same time as magnetic fields. So like the transmitting antenna emits electromagnetic energy, and then the receiving antenna takes that energy or sample that energy, but it has to be AC for it to work. Through it, right?
Okay. Or
At high frequencies.
Yeah.
So different frequencies have different propagation characteristics. So like how far you want to go, and how much power you want to use. And then, but usually you start out with like some DC power to generate the RF, and then you transmit it, over the airwaves.
Yeah.
And then you receive it, and then you use like a detector or the modulator to convert the received RF into like either a lower frequency AC signal, like the less information, or in some instances you just care about whether the RF is on or off, in which case you just kind of get like a DC output, that varies as well.
Okay. What about like open and closed circuits? Like when would you use an opened and when would you use a closed one?
Well, I'm trying to think like, I guess it's like so to us, like a short circuit, it's kind of a bad thing, because you wouldn't want it to be a short circuit, because that kind of implies that something got shorted out, right?
Mm-hmm.
So basically a short circuit is, a path for electricity to go through that has very low resistance, and that may or may not be good.
Okay.
An open circuit is a path that has very, very high resistance, so the current is negligible. So like for a short circuit, current would be very high potentially.
Mm-hmm.
So we probably use like a fuse or circuit breaker to protect yourself from short circuits. And so like once the current goes over some safe limit, the circuit breaker will open up the path and then basically shut down the equipment so it doesn't cause any damage.
Okay.
So short circuits are usually bad. Open circuits
Bad.
are usually bad if it means that something isn't connected. So, that's actually kind of a diagnostic tool. So one of the things we'll do is like when we get something that we need to repair, we'll actually like measure out, so it'll be, basically like a box, have like inputs and outputs. And so one of the things that we commonly do is we measure, what all the inputs are, the impedances of all the inputs and outputs. And then if we've like fixed or diagnosed this before, we know what they should be. And so one good way to tell us like something's broken is like when you're measuring the impedances that maybe one of the inputs is like short circuited, it should be.
Then you can figure out what to
At
do.
least have an idea of what part of the inside of the box to look at.
What is electromagnetic induction?
So electromagnetic induction, we would use that, for example, in a transformer. So we would have like one coil, one side would have a coil, it would generate a magnetic field that varies, and then coupled, either through air or like a iron core, there's another coil that then, takes the coupled magnetic field and then generates like a potential on the output. So we use that to change, for example, if we want to increase or decrease the voltage for a circuit. So if we have something that's a high voltage on one side and a low voltage.
Okay.
So it's kind of nice because it's relatively low loss, so you get like a small voltage, but the power capacity is about the same, but like a lot more current on the secondary side. So that's one application that we use like, in the coupling.
That's very good.